Linear equations appear in many real-life situations. Let's take a look at one. The calories burned while walking, C, can be approximated by C equals 70D, where D is the distance walked in miles. Graph the equation and use the graph to estimate the number of calories burned for a 5-mile walk. So to graph this equation, and it is a linear equation because it's in the form of y equals m times x plus b, is the standard form of a linear equation. Now we've replaced the y and the x, and there's some values missing, but it's still nonetheless, we'll find that it does graph, in fact, and follows a linear equation model. So picking some values so that we can graph this, we will replace D with chosen values. If we don't walk any distance at all, C will equal 70 times D, which is 0, which is 0. Makes sense? If you don't walk, no calories are burned. If we choose 1 for D, and replace D with that 1, simplifying, we end up with 70. So 1 mile is equivalent to 70 calories burned. We're now going to graph this information and recognizing that we have much smaller values for our distance and our resulting values for the calories burned are going to be much larger numbers. The scale on the horizontal axis may be different from the scale on the vertical axis, which is the case here. Within each axis, however, the number of units each mark represents must be constant. So I've already filled in, or at least the 10 on our scale here, with 1, 2, 3, and so on, being our distance in miles for the horizontal axis. And then we're going to graph calories on the vertical axis. And we will use a different scale because 70 is going to be off very quickly if we had actually used 2 times 70 is 140, so we can see that the number of calories is going to increase substantially here. So 100, 200, and so on for our scale would be appropriate here. And let's plug in those values. The first one, the ordered pair was 0, 0. That's here. The other point was 170, and I'm going to approximate where 70 is on the graph. Using a straight edge, we'll connect those points for a representation of the calories burned with the distance walked. And the problem asks, let me slide this back down, to estimate the number of calories burned for a 5-mile walk. Now we could use the equation and simply put in 5, but just to show how the graph can answer that question, here would be a distance of 5 miles. We'll read it up to where it intersects the line and then bring it across horizontally to determine the value. And it appears when the distance is 5 that approximately we have 350 calories burned with that amount of exercise.